Leetcode problem 3315. Construct the minimum bitwise array 2. So for this problem, we are giving an array nums consisting of n prime integers, and you need to construct an array answers of less n, so such that for each index I, the bitwise OR of answers I and answers I plus 1 is equal to nums I. Yeah, so what is the idea? Yeah, so for any numbers, so for example, if this number is 2, so 2 is a prime number and 2 is even, is that possible? Yeah, we're gonna use x or x plus 1 equal to 2. Is that possible? Yeah, so this is not possible because for any number, if this is odd number plus 1, it's going to be even. Odd number or even number, finally it's going to be odd. Yeah, and similarly, if this is even and this one going to be odd, and even or odd, and finally it's going to be odd. It can never be 2. Yeah, it can never equal to 2, so it's not possible. Yeah, so this means for the first one, if it is equal to 2, definitely it is not possible. And for all other numbers, as it is prime numbers, so for all other numbers, definitely it is not even number, so it's gonna always be possible. Yeah, so the idea is that we need to understand how to calculate this x or x plus 1. So let me just give an example. So we have something like 1 0 0 0 1 1. Yeah, so for this number, if we were to plus a 1, what's going to be the final result? So the final result, if we plus a 1 and then x plus 1 or x, what's going to be the final result? The final result, we're going to set the low bit of 0. We're going to set the low bit of 0 to 1. So we're going to set the low bit, this is the low bit of 0. From the from right to the left, we're going to set this low bit 0 to 1. So it's going to be 1 0 0 1 1 1. Yeah, but how did we calculate it like this? Yeah, so first of all, we're going to plus 1. So this plus 1. Yeah. So x plus 1. And then we're going to use OR operation. So it's going to be this one. Yeah. So if we were to do the operation for any number, if we were to do the x or x plus 1, definitely we're going to set low bit of 0 to 1. Yeah. Now we are giving this number 1 0 0 1 1 1. So for example, we are giving this number and we are checking this number x. So what's going to be this x? Yeah, as we can get it from setting the low bit of 0 to 1. And similarly for here, first of all, we're going to find the low bit of 0 first. Yeah, and then from the 0 to the right side, we're going to find the first one. If it is 1, we're going to set it to 0. So this is 1 0 0 1 1. So this is going to be the original. Yeah, this is going to be the original number. First of all, we're going to check the low bit of 0. And from the 0, we're going to go to the right side. If we find 1, we're going to set it to 0. Yeah. We can also do it like others. So for example, we can set this one to 0. This is also okay. But this is not the smallest number because 1 0 1 is larger than 0 1 1. Yeah, this is also possible. Let me just do it. So for example, 1 0, we're going to plus 1, so it's going to be something like this. And then we're going to use and then we're going to use the OR operation. Let me think about it. Yeah, so if we are giving this number, we're going to set this 1 to 0. Yeah, so this is okay because this 1 plus 1 is going to be 1 0 0 1 0 0. And the final answer is going to still be this one, 1 0 0 1 1 1. Yeah, it's going to still be this number. But currently, we don't want to do it like this. So if we were to set this number, though this is a 0, and from the right side we were to set this number 1 to 0. So what's going to happen is that we set it to 0, and we still do the operation plus 1. So it's going to be 1 0 0 1 1 0. Yeah, and then we're going to do the OR operation. It's going to be 1 0 0 1 1 1. Yeah, so from this number we can still get it the final result 1 0 0 1 1 1, but this number is not the minimum number. It has to be 0 1 1. So this is why we're going to first find the binary number, find the low bit of 0. It means from the right to the left, we're going to find the first 0, and then from the 0 to the right side, we're going to find the first one, and we just need to set the first one to 0, and this is going to be the final answer. Yeah, so let me just try to use another example. So if we have 3, so 3 is going to be 1 1. Yeah, so before it's going to be something like 0 0. Yeah, so this number is 3. How can we find it's going to be 1? First of all, we're going to find the first 0, it's going to be here. Yeah. Then at the right side, we're going to set the first 1 to 0. It's going to be 0 0 1. So the final answer is going to be 1. And let's just use a 5. So 5 is going to be 1 0 1. So we're going to find the first 0. So 0 is here, right? And for 0, from the right side, we're going to find the first one, and then we're going to set it to 0. It's going to be 1 0 0. It's going to be 4. And similarly for this 7. We find the first 0, it is here, because at the right side there's no 0. And then we're going to set from the 0 to the right side, if there's a 1, we're going to set this 1 to 0. So the final answer is going to be 1 1, which is going to be 3. Yeah. But how can we calculate it like that? Definitely we can use many for loops to check. Yeah. So for example, we are giving this kind of binary number. Yeah, we're going to find from the right to the left side, for any number from the right to the left side, we're going to find the first 0. Yeah, because if this number is not 2, not even number, definitely from the right side there's a 1. And then we're going to set this 1 to 0. Yeah, it seems a lot of a for loop and a lot of tags, but in bit manipulation, we don't need to do such kind of tags. We can directly use the bit manipulation to calculate it. Yeah, so for example, we have such numbers like 1 0 0 1 1. So basically we want to set this one to 0. But how can we set it? Yeah, so first of all we're gonna do the bitwise NOT operation. If the bitwise NOT, it's gonna be something like 0 1 1 0 and 0. And then we're gonna do the low bit operation, LB. Low bit operation, we're gonna find this one. So this 1 is here. Now we find the low bit. It's going to be 1 0 and 0. Yeah. And then we're gonna use this low bit, because we find the low bit. It is 1 0 0, and we're gonna shift 1 bit to the right for the low bit. It's going to be 1 0, and then we're gonna use 1 0 XOR with the original number, with this number. Yeah. So this means after this one, everything gonna be kept the same. So this is 0 XOR 1, it's gonna be 1. If it is 0, it's gonna be 0. We're gonna keep the same. But for this bit, this is exactly what we are checking. If it is definitely for the low bit, this is gonna be 1, and definitely this is also 1. So this means we can set this 1 to 0 according to the low bit idea. First of all, we're going to calculate the low bit, and then we're going to shift 1 bit to the right, and then we're going to use XOR with the original number, and we definitely set this 0 to 1 and keep all other numbers the same like before. So we're going to check the numbers one by one. So for in a enumerate of nums, first of all, if this n equal to 2, this means it is even. It is not possible, so nums I gonna equal to -1. So otherwise, for all other prime numbers, we can calculate it. So as I said before, first of all, we're gonna use our low bit. So t gonna be equal to a NOT of this number, and then we're gonna check the low bit, which is gonna be t add negative t. Yeah. Now we're gonna shift the low bit and XOR with the original number. So nums I XOR equal to this low bit, and we're gonna shift one bit to the right. So finally we're gonna return the nums. Yeah, we just do it in place because we didn't use any extra memory, and the time complexity gonna be just ON. Yeah, as you can see, it works. Now let me just submit it to check if it can pass. As you can see, it passed for all testing cases, and it's pretty fast. Now for this problem, we are giving this nums length is 100, and we are calculating using this kind of algorithm, using the NOT and low bit. So normally if the nums length is 10 to the power 5, it is still okay, but for this problem it is just 100, so the time complexity is ON. I think that's all about it. Thanks for watching, see you next time.